Hello and welcome back to yet another session of Target JEE Advanced brought to you by BYJU's. In today's session, we are going to look at a mathematics chapter. The first of the three integration chapters, we look at indefinite integrals today. In this session, I'll analyze indefinite integrals from the JEE main and advanced examination points of view, look at some of the important topics from the examination point of view, and finally, look at the all-important problem solving which will help you identify the types of questions which come from indefinite integrals and also give you a flavor of how interesting indefinite integral questions can be. So, indefinite integrals is the first chapter of integration, and remember, integration is a very important section from the examination point of view. Plenty of questions come from integration in the examination. But these questions which come from integration are generally not from indefinite integration. Definite integrals, area under the curves, and differential equations, these fetch a lot of questions from integration, but indefinite integrals as such do not fetch many questions. If you look at the advanced examination, in the past 6 years, not one question has directly come from indefinite integrals in the examination. Of course, in the main examination, 2013 until 19, every year one question has come in the examination. But again, indefinite integrals is not a chapter which has a lot of weightage from exam point of view. But does that make this chapter any less important? Well, on the contrary, that makes this chapter very much important, because this chapter is the fundamental to all of the integration that you'll be looking at in your 12th standard. So definite integrals, area, and differential equation. In order to solve that, you need to have a very good understanding of indefinite integrals. So people tend to not pay a lot of attention to this chapter because no direct questions come from here, but they forget the fact that if they don't understand this chapter, they cannot understand the subsequent chapters well, and those subsequent chapters have a lot of weightage. So you better focus on this chapter and understand this chapter, not from exam point of view, but for understanding the whole of integration. So the topics in integration which are really important are topics such as integration by substitution, integration by parts, and integration by partial fractions. Integration by substitution is the single most important section in this chapter. Integration by substitution has wide number of techniques. There are various different substitutions that you can make in order to arrive at the solution. If you look at the main paper, 2013 the question was based on integration by substitution. 2014 the question was integration by parts. 2015 was again a substitution type of 6 question. 2016 it was again a substitution type of question wherein you had under root terms appearing in the denominator, and this substitution was not a trigonometric substitution that you had to do. So that was again another variety of substitution question. 2017 we had a recurring type of integral. They had given I1 as something, I2 as something, and you had to find out I4, I6. So a general expression for I was given, and you had to find out I4, I6, and then do some things with those things. So that was a recurring type of integration. 2018 was a trigonometric substitution type of integration, and 2019 was again a question where you had to do completion of squares and then use a trigonometric substitution. So if you see, every year the question had something to do with the integration by substitution. So integration by substitution is the single most important section of this particular chapter. So we will quickly look at the concepts in this chapter and solve a lot of questions, and inevitably in most of the questions you will see that there's going to be some integration by substitution. So here are the important concepts from indefinite integration. So the chapter on indefinite integral, which is the first chapter of integration, introduces integration to you through the fundamental integration formula. Well, integration is introduced as the opposite of differentiation. You begin by looking at the derivative of a function. If the derivative of a function is f of x, if a derivative of g of x is f of x, then integral of f of x will give you g of x plus a constant. So when you integrate a function, when you integrate the derivative of a function, you will get the function plus a constant. So you get a family of functions. So based on this, we develop a lot of standard integration formulae. There are a number of standard integration formulae, and it's worthwhile remembering all these standard integration formulae so that you don't have to sit and derive them in the exam hall. Of course, then we look at properties of indefinite integrals. What happens if there is a constant multiplied to the function inside the integral? What if you have a sum or difference of functions in an integral? What if you have a derivative of a function divided by the function and you have to integrate that? Well, to be very honest, it's not something that you need to remember as a property, because using substitution you will actually end up getting the answer as log of the function plus a constant for this particular integral. But it's worthwhile remembering it as a property also. Again, it will do some time saving in the examination hall. Then there are some more formulae. Again, all these formulae can be easily derived using a substitution method of integration. I'm repeating that the substitution method of integration is a very important thing. Number of standard results have been derived actually using the substitution method of integration. So let's look at integration by substitution. So in order to evaluate, let's say, an integral of the form f of g of x multiplied by g dash of x dx, what you can do is you can substitute for this g of x as a new variable t. So then g dash of x dx will be nothing but dt, and then you integrate for f of t dt. Integrating f of t dt is much easier than integrating f of g of x multiplied by g dash of x dx. So that's what we do in integration by substitution. We make life very easy by substituting a variable, and then at the end of the process, once you've found out the value of the integral, you back substitute for the variables and finally present the answer in terms of the variable which was initially present in the question. So integration by substitution is to make life easy for you. It helps you convert non-familiar integration objects into familiar integration objects. That's the whole objective of integration by substitution. There are some very standard substitutions that you must remember, especially in trigonometry. You have a lot of standard substitutions. There is a plethora of those available. I've actually noted down a few of those for you. There are many of such substitutions which are available, and the more number of questions you solve, the more variety of questions that you come across, you will actually be more familiar with the different types of substitutions that are there. There are lots and lots of varieties of questions available here. So you can actually solve n number of varieties and still not be done with all the different types of substitution type of integration questions. Then we move on to another very interesting formula, which is called as integration by parts. Now, integration by parts has a standard algorithm. Now, that actually is the opposite of the product rule of differentiation. So if you had the product rule of differentiation, the opposite of that is actually the integration by parts. When you have a product of two functions, how do you integrate that? So in an integral which has a product of two functions, you choose one function as the first function and the other as the second function, and then go with this algorithm, which is the first function is retained and then you integrate the second function minus the integral of the differential of the first function multiplied by the integral of the second function. So if you see in this whole process, you are never actually integrating the first function. You're only integrating the second function, and the derivative of the first function is taken. So when you have a function which is very complicated to integrate, you can choose it as the first function and never actually integrate it as such. So for this, there is a small rule. You always choose the first function in this particular order. If there is an inverse function, inverse trigonometric function, you choose that inverse trigonometric function as the first function always. In the collection of inverse trigonometric or with logarithmic function or an algebraic or a trigonometric or an exponential functions. So the order of choosing the first function is inverse trigonometric, logarithmic, algebraic, trigonometric and exponential. And there is a mnemonym for this, which is I late, I for inverse, L for logarithmic, A for algebraic, T for trigonometric and E for exponential. So this is the order of choosing the first and the second function to assist you in the process of integration by parts. If you switch the order, integration by parts will make life more complicated than the existing situation. So never switch the order, unless of course you have a trigonometric and exponential. In the end you have trigonometric and exponential. Well, those actually can be switched. That's the only case wherein you can switch the order. Otherwise, you actually are not supposed to switch the order. Finally, there's another important portion to this chapter, which is integration of rational functions by partial fractions. You've already seen partial fractions in algebra. So if you have a rational function wherein the degree of the numerator is less than the degree of the denominator, then sometimes you can use partial fractions to simplify that expression into forms that are very easy to integrate. So that closes this chapter. So in terms of the number of concepts, there are a few concepts: substitution, paths, integration of rational functions by partial fractions. But substitution itself is a notion. There are a huge number of techniques available there. So this chapter becomes very, very big because of integration by substitution. Now let's have a look at some questions, and inevitably in most of the questions I have already mentioned, you will use integration by substitution. Here is the first question. Now in this first question, we've been given an integral and they've told that this integral is equal to something else. Now the answer is in terms of two constants a and b, and the objective is to find out the values of a and b and then find out what is mod of a minus b. So what's the integral that has been given to us? The integral is integral of x square plus sine square x divided by 1 plus x square, all multiplied by secant square x dx. And it has been told that this integral is equal to a cot inverse of x plus b secant x divided by cosecant x. So now there is the a and the b whose values you have to find out. First of all, now look at this question. We have a term here, x square plus sine square x all divided by 1 plus x square multiplied by secant square x. How do you go about this? When the integration question is so difficult, what we do is we divide and conquer. We take terms individually and look at individual terms and conquer. So now, there is a 1 plus x square in the denominator, there is an x square in the numerator. So if I add 1 to the numerator, I will get that 1 plus x square. But to negate the addition of 1, I'll have to subtract 1. So what I am going to do is I'm going to add a 1 and I'm going to subtract a 1. So now I have a 1 plus x square divided by 1 plus x square, which is nothing but 1. So my integral is going to convert to the integral of 1 times secant square x, which is secant square x dx. Now I know how to integrate secant square x, so that is the reason why I did this. And then there is sine square x minus 1. What is sine square x minus 1? Sine square x minus 1 is nothing but minus cos square x, because 1 minus sine square is cos square. So sine square x minus 1 is minus cos square x. So I have a negative of a cos square x into secant square x divided by 1 plus x square dx. Now, what is secant? Secant is 1 upon cos. So cos square x and secant square x, they cancel out. So give me 1 upon 1 plus x square with a minus sign. I again know how to integrate this. So see, divide and conquer helped us to integrate this very easily. I had to split the two terms, do a little bit of mathematical manipulation, and now I have arrived at two terms which I know to integrate very easily. This is a golden rule of integration, divide and rule. So now integral secant square x dx is nothing but tan x. And integral of 1 by 1 upon x square is actually tan inverse of x, but there's a minus there, so I can write this as integral of minus 1 upon 1 plus x square, which is nothing but cot inverse of x. The reason why I'm going to write it as cot inverse of x is because look at the answer. The answer is a cot inverse of x plus b secant x by cosecant x. So writing it in terms of cot inverse of x is going to be very useful. And for the sake of completion, there is actually a constant of integration, but that constant is very important, so that constant is going to be there. So now I know what is a, correct? Because if I compare it with a cot inverse of x plus b secant x by cosecant x, with the answer I get the value of a as equal to 1. My a is straight away 1. What about b? Now b is the coefficient of secant x divided by cosecant x. I do not see a secant by cosecant, so let's try and simplify secant by cosecant. Secant is 1 upon cos, cosecant is 1 upon sine. So that is effectively nothing but sin x upon cos x, which is nothing but tan x. So this clearly means that they have written tan x in a very fancy way, and we have a tan x in our solution, which means that D is also equal to 1. If A is 1, B is 1, A minus B is 0, and mod of 0 is 0. So the correct answer to this question is nothing but 0. Very simple question. At first, it looks like a monster, but then if you divide and rule, then the question is very, very simple to solve. Now let's look at a question which needs integration by parts to arrive at the answer. Here's the question. So this is a standard integration by parts type of question. So you have to integrate e power negative 3x multiplied by sine 4x dx. Well, you have an exponential function and a trigonometric function, a product of that. As soon as you see that integration by parts strike to your head, and when it's integration by parts, we have the famous acronym. I'm sure all of you know this acronym in some form or the other. It's the famous acronym ILATE. So now what is ILATE? Well, ILATE stands for inverse trigonometric, logarithmic, algebraic, trigonometric, and exponential. So if there is a product of any of these functions, you take the first function and the second function in this particular order. But hang on. Do you know one very interesting fact? Trigonometric and exponential functions, it actually doesn't matter which one you choose as the first and which one you choose as the second. If you have a product of trigonometric and exponential functions, you can choose either one of them as the first and either one of them as the second, and you will still arrive at the correct answer. If you don't trust me, let's do it the other way. So according to the ILATE acronym, you have to do trigonometric as the first function and exponential as the second. I'm going to choose exponential as the first function and trigonometric as the second function and show to you that this works as well. So first function is going to be retained as it is in integration by parts. So e to the power negative 3x. Then you have to integrate the second function, integral sine 4x dx. What is integral sine 4x? It's nothing but negative cos 4x divided by 4. Correct? Minus the integral of the differential of the first function, that's going to be a negative 3 e raised to negative 3x multiplied by the integral of the second function. Well, the integral is a minus cos 4x, so I'm going to make this a plus, but there's a minus, so overall we are going to still get a minus. So that's going to be e raised to 3 e raised to minus 3x multiplied by cos 4x divided by 4. So I'm going to keep the 4 here, and this has a dx now. So I've got the first term, which is going to be e raised to negative 3x times minus 4 cos 4x divided by 4. We have to not touch that ever again. So my I has one term already fixed, but there's one more integral to be solved. So I'm going to just solve that integral for you now. Okay, nothing else. So again, I have a product of an exponential and a trigonometric, and again I'm going to switch the order. I'm going to take the exponential as the first function, trigonometric as the second function. So I have to go to keep the negative 3 over 4 common outside, and then use integration by parts for the second time. I get e raised to negative 3x, the first function, that's going to be as it is. And then I have to integrate the second function. The integral of the second function is going to be sine 4x divided by 4, because now the second function is cos 4x. And from this I have to subtract, well, the integral of the differential of the first function, that's going to be e raised to negative 3x. That's going to give me a minus 3 e raised to minus 3x. And then the integral of the second function, which is nothing but sine 4x divided by a 4, and that is a dx here. So now you see how is this going to be. You will always end up with an integral whatever happens, but there's a catch. Now if I take this negative 3 over 4, this becomes a positive here, and e raised to minus 3x sine 4x dx has to be integrated, and that is nothing but I itself. So my I is this function here, e raised to negative 3x multiplied by minus cos 4x by 4, and then I have minus 3 by 4 e raised to minus 3x sine 4x by 4 plus 3 by 4 I. Right? That itself is I. Integral of e raised to negative 3x sine 4x dx is nothing but I. So I have this expression which is completely devoid of integrals. Now I bring the 3 by 4 I over onto the other side. Well, in fact, I have to bring 3 by 4 times 3 by 4. I have to bring 9 by 16 I over to the other side. And if I simplify that, this becomes a very neat and clean 25 by 16 I is this particular expression here. And don't forget the constant of integration. So we will keep a constant of integration at the end of this answer. So that's going to be the answer to this question. But of course, we just need the value of I, so you have to divide throughout by 25 by 16 and taking common factors or LCM on the right hand side and doing all the mathematical manipulation, you will arrive at this answer. So the final steps, they are just mathematical manipulation. The beautiful part of this question is the fact that your I will have an I inside it. Whatever you have to integrate, you will actually get that integral again. And then all that you need to do is a little bit of algebra. So I have shown you that you can actually switch the order of trigonometric functions and exponential functions in the ILATE, which is a standard procedure that we follow for the integration by parts method. So you switch the trigonometric and exponential functions and still nothing really changes. A very cool fact, isn't it? So you can actually test if I am correct or not by not switching and taking the trigonometric as the first function and the exponential as the second function, and you will see that you will still arrive at the exact same answer. Now, following that question on integration by parts, I'm going to solve another question which is going to make use of integration by parts. So that's a small hint for you to guess the method of solving this question. So this is the question. So now in this question, we have a pretty complex looking expression that we need to integrate. We have to integrate x square multiplied by x secant square x plus tan x divided by x tan x plus 1 the whole square dx. Now you must be wondering, what similarity does this have to the previous question and how am I going to make use of integration by parts? I'm going to show it to you. But before that, this looks like a standard substitution question, isn't it? You have something in the denominator, you have a complex looking expression in the numerator. So let's try and see if we can replace the denominator or the numerator as a differential of something. So I'm going to consider my denominator here as some other variable t. So I'm going to consider my t as x tan x plus 1. What happens if I consider a t as x tan x plus 1? My dt will be nothing but x secant square x plus tan x and all into dx, correct? Now look at the question. In the numerator, you actually have x secant square x plus tan x dx. But in addition to that, you have an x square. Now, that is a little bit of a problem. So what we will do is we're going to rewrite this as x square multiplied by x secant square x plus tan x divided by x tan x plus 1 the whole square and all of this dx. Now see, this second function here, if this is my second function, this is of the form dt divided by t square. And I know to integrate dt divided by t square. So what is integration by parts? In integration by parts, you never integrate the first function. You only integrate the second function. So if I know to integrate the second function, I can actually use integration by parts. So I'm going to make use of integration by parts. So this is something that's a little difficult for you to visualize, and that's why I'm solving this question and giving you a little more details than required. So this is where we are going to make use of integration by parts. I will be the first function as it is and the integral of x secant square x plus tan x divided by x tan x plus 1 the whole square dx minus the integral of the differential of the first function, that's going to be 2x, multiplied by the integral of x secant square x plus tan x divided by x tan x plus 1 the whole square dx. So, and this entire thing is going to have a dx here. Don't forget that dx. So now we need to integrate x secant square x plus tan x divided by x tan x plus 1 the whole square. If I consider x tan x plus 1 as t, it is nothing but integral of dt over t square. And we know what is integral of dt over t square. Integral of dt over t square is nothing but negative 1 over t. So that implies that integral which we had to compute was nothing but negative 1 over x tan x plus 1. Very beautiful, isn't it? So now I know how to compute that integral and I found out the value of the integral. Plug it back into your expression for I, and what do you see? You will see that your I value is nothing but x square multiplied by negative 1 over x tan x plus 1 plus, we still have an integral. In fact, it's not a plus, it's a minus the integral of, it became a plus because of that negative 1 there. You have the integral of 2x into minus 1, so that becomes the plus there, into x tan x plus 1 in the denominator, this dx. So now we have to integrate this second function here. This is the integral that we need to concentrate on. So this is a very lengthy question. We've already done integration by parts. We've already done integration by substitution. We are still not at the end of this question because there is one more integral that we need to evaluate. And 2x divided by x tan x plus 1, I am now going to rewrite things in sine and cos. So I can write this as 2x cos x divided by x sin x plus cos x, correct? I can rewrite that if I write tan by as sine by cos and then take a denominator onto the top. All this will happen. Now what do? I am going to consider x sin x plus cos x as another dummy variable that's going to be t. If my t is nothing but x sin x plus cos x, I'm going to consider my t as x sin x plus cos x. So if my t, the new t, remember, do not confuse this t with the old t we considered. This is a new t. If my t is x sin x plus cos x, then my dt will be, use the product rule, that's going to be x cos x plus sin x, and then the derivative of cos x, which is minus sin x and dx. Beautiful, isn't it? The sin x's will cancel out and dt is nothing but x cos x dx. And that is exactly what is that here. So this means that I can now easily integrate, because this will be nothing but the integral of 2 times dt over t, which is nothing but 2 log of t, right? So if I substitute the value of t as x sin x plus cos x, I get the final answer as negative x squared divided by x tan x plus 1 plus 2 times the log of x sin x plus cos x plus, of course, the constant of integration. A very long question, lots and lots of integrations to happen. You saw that there was integration by substitution couple of times, then there was integration by parts, and then of course the first trick was to understand that this is an integration by parts question. This is actually a very difficult question, and I hope such questions don't come in the examinations. Then if they come, this is how you solve them. After having seen a couple of very interesting questions involving integration by parts, let's look at another variant of question. So in this question, we have to find the integral of e power x multiplying 1 plus sin x plus e power negative x multiplying 1 minus sin x, all divided by 1 plus cos x dx. Now, there is e power x, there is a trigonometric function, so you will be tempted to solve it using integration by parts, but that's not how we're going to solve it. We're going to make use of another very interesting result with e power x. That is e power x multiplied by a function plus its derivative. When you take an integral of this, you're going to get e power x times the function. So, integral of e power x multiplying f of x plus f dash of x dx is nothing but e power x f of x. So we're going to use this, of course, the plus constant of integration, that's always there. We're going to use this result here, but in order to do that, we are going to rewrite our expression in a slightly different way. So I'm going to write I as integral of Now I'll keep the e power x plus e power minus x together. That is what I get when I multiply e power x to 1 and e power minus x to 1 plus e power x minus e power minus x multiplying sine x, all divided by 1 plus cos x dx. Now I've rewritten my expression in this way, and that is for a reason. What I do next is I am going to write 1 plus cos x as 2 cos square x by 2 and sin x as 2 sin x by 2 cos x by 2. Again, these are standard things that we do as soon as we see such terms in an integration question. So these should come to you very organically in integration questions. So now look at what do we have. I is nothing but the integral of e power x plus e power minus x, and that is being divided by 2 cos square x by 2. That is nothing but 1 half secant square x by 2, right? Plus you have e power x minus e power minus x. What is that multiplying? Well, the 2's will cancel out. One of the cos x by 2 will cancel out and you'll be left with sin x by 2 divided by cos x by 2, which is nothing but tan x by 2. Now this makes a lot of sense to me because I have tan x by 2 and I have secant square x by 2. Now the derivative of tan is nothing but secant square, so I can see a function and its derivative all multiplying e power x's and e power minus x's. So this is very beautiful. So now what I do is I am going to split up the e power x's and e power minus x's and group secant square and tan together in this particular way. E power x is going to multiply 1 half secant square x by 2 plus tan x by 2 dx. And the other integral will be e power minus x multiplying half secant square x by 2 minus tan x by 2 dx. In a very beautiful way, I have rewritten everything. So what I will do is I'll take the halves common out from both the sides. I will take half common out from both the integrals and I will rewrite this in a further way so that I can clearly see function and its derivative. So I can rewrite it as half of integral e power x secant square x by 2 plus 2 tan x by 2 dx plus e power minus x of secant square x by 2 minus 2 tan x by 2 dx. Now if I consider this as my first function, f of x, if 2 tan x by 2 is my f of x, then what is f dash of x? Well, f dash of x is 2 times secant square x by 2 into half. So the 2 and a half cancels and this is nothing but f dash of x. So I have e power x multiplying f of x plus f dash of x, and I know how to integrate that. So the integral of that will be nothing but e power x times the function itself, which is 2 tan x by 2. Now let's look at the other case. I'm going to consider negative 2 tan x by 2 as my function f of x, or in this case another function g of x. Negative 2 tan x by 2 is g of x. So what is g dash of x? G dash of x is negative 2 multiplying secant square x by 2 into a half. The half and the half cancels, which give me a negative secant square x by 2 as the derivative. So this is nothing but minus g dash of x. So I have e power negative x multiplying g of x minus g dash of x, and we again know how to integrate this. It's nothing but e power negative x multiplied by the function itself. So my final integral is 1 half of e power x multiplied by the function, which is 2 tan x by 2, plus e power minus x multiplied by the function, which is minus 2 tan x by 2. So the half is going to cancel out with all the 2's in the numerator, and I get e power x minus e power minus x tan x by 2 plus of course the constant of integration. Again, a beautiful variant of integration question, another very wonderful variety of question wherein we made use of the fact that e power x multiplied to a function plus its derivative, or e power minus x multiplied to a function minus its derivative, is very, very easy to integrate. So there are a lot of variants of questions in indefinite integration, and it's really worthwhile to go through all these different variants of questions in indefinite integration. Let's look at one more variant of integration question here. Now, this question is a very standard integration by substitution type of question. So as soon as you see this question, you should be very happy because this is a question that all of you must know how to solve. And remember, such questions have come in the past examination, so you never know, another year such a question might again appear and you know already how to solve this question. So you should be able to get the marks that are on offer from this question. So the question is, you have to integrate x raised to 4 multiplied by 5 plus 4x divided by x raised to 5 plus x plus 1 the whole square. That's what you need to integrate in this particular question. So now as soon as you see this question, you should understand that this is a substitution type of question and we need to substitute the denominator as some variable, and then we need to have the numerator as the derivative of the denominator. But before doing all that, in such questions there is some mathematical manipulation that is mandatory. So the mathematical manipulation is, you're going to take this term here, which is the highest power of x, out of the bracket in the denominator and then divide the numerator with that term. Because as of now, the denominator and the numerator seem to have no connection at all. But once you do that, the numerator will become the derivative of the denominator, or it will become a factor of the derivative of the denominator. So we're going to arrive at that. So the first thing I do is take x power 5 common out of the square in the denominator. So I get x raised to 4 times 5 plus 4x dx divided by, when I take x raised to 5 common out, because there is a square, it becomes x to the power 10, and then I have x raised to 5 divided by x raised to 5, which is nothing but 1 plus x raised to minus 4 plus x raised to minus 5 the whole square. Now the derivative of 1 plus x raised to minus 4 plus x raised to minus 5 will have x raised to minus 5 and x raised to minus 6. I don't see that in the numerator, but there's an x raised to 4 and x raised to 5 in the numerator. So if you expand your numerator, you are going to get 5x raised to 4 plus 4x raised to 5, and that's divided by x raised to 10. I'm going to keep the x raised to 10 in the numerator itself, and of course the denominator is 1 plus x raised to minus 4 plus x raised to minus 5 the whole square. Now x raised to 4 divided by x raised to 10 is x raised to minus 6, and x raised to 5 divided by x raised to 10 is x raised to minus 5. And now things are making sense to me, because if I consider the denominator as my t, my dt is going to be negative 4x raised to minus 5 negative 5x raised to minus 6 dx, and this is nothing but the negative of the numerator. So now my integral is nothing but negative of integral dt over t square, and I know how to integrate this. Negative of integral dt over t square is nothing but 1 by t. That's the constant of integration. So the value of the integral is nothing but 1 by t plus the constant of integration. T is nothing but 1 plus x raised to minus 4 plus x raised to minus 5. So the value of the integral is 1 by 1 plus x raised to minus 4 plus x raised to minus 5 plus the constant of integration. And definitely in these questions, this will not be one of the options, because you have to go back to the terms which have positive powers in the denominator. So what we will do is multiply the numerator and denominator by x raised to 5. So if I multiply the numerator and the denominator by x raised to 5, all the negative powers will vanish, and I get the value of I as x raised to 5 divided by x raised to 5 plus x plus 1 plus the constant of integration. So this is the correct answer to this very, very common substitution type of question in indefinite integration. Now let's look at yet another type of substitution question, but this question it's not very obvious what the substitution has to be. So let's look at the question. So in this question, we have to find out the integral of 1 divided by 3 plus 4x square times under root of 4 minus 3x square, dx. So if we had in the denominator a term such as under root of 1 minus x square, then the general substitution we make is x square equal to sine square t, or x is sine t. This way what we have is under root of 1 minus sine square t, which becomes cos t, and we do away with the under root term. Here also in this question we have an under root and an x square inside the under root, but it's not as trivial as under root of 1 minus x square. So what is the substitution that we are going to make? So we are going to make a substitution which is 3x square equal to 4 sine square t. So this way what happens is the under root term becomes under root of 4 minus 4 sine square t. You can take the 4 common out, you get 2 times under root of 1 minus sine square t, which is nothing but 2 times cos t. So now we can handle the under root with this substitution. So let's try and find out what is dx corresponding to this substitution, and also there is another term 4x square. So let's try and find out what is 4x square also in terms of this substitution. So if 3x square is 4 sine square t, that would imply that x is nothing but 2 over root 3 sine t, isn't it? So now we can find out what is 4x square. 4x square will be nothing but 16 divided by 3 sine square t, and dx will be nothing but 2 by root 3 cos t dt. So we are now going to substitute everything in this particular integral, and we will rewrite this integral to get I is equal to 2 by root 3 cos t dt divided by 3 plus 16 over 3 sine square t, that was 4x square, and under root of 4 minus 4 sine square t. So now this term I've already explained to you. This term will be nothing but 2 cos t. So my integral is now going to be simplified. Well, let's try and simplify. The 2 cos t from the numerator and the denominator will cancel out. So I have a 1 over root 3 in the numerator. That's all, nothing else. But here you have a 3 plus 16 over 3 sine square t. If you take a common denominator of 3 here, you get 9 plus 16 sine square t divided by 3. So this 3 and this root 3 will cancel out to give me a root 3 all in the numerator. So eventually I am going to get root 3 dt divided by, well, I have 9 plus 16 sine square t. So I have to integrate this expression now. So see, with that one substitution, my question has simplified many folds. So the under root terms are gone and a lot of complex terms are gone, and now I just have root 3 dt divided by 9 plus 16 sine square t. Now what do we do? It seems like we've again hit a dead end, because we cannot continue with this because we don't know how to integrate this expression. So what I'm going to do is I am going to divide by cos square t both the numerator as well as the denominator. Because what happens if you divide the numerator by cos square t, you're going to get a secant square t, and sine square by cos square is nothing but tan square, and we know the derivative of tan is secant. So maybe we might have to make another substitution, but this seems like progress. So what I will do is I am going to make this substitution to get the expression of I modified. So now my integral becomes integral of root 3 secant square t dt divided by 9 secant square t plus 16 tan square t. Now, if we just had tan square in the denominator, I could have made a substitution for tan t as some other variable, and the numerator would have been a multiple of its derivative. But there is a secant square also in the denominator, but we know how to convert secant square to tan square. I can write secant square as 1 plus tan square t, and then my integral will change to this particular one, under root 3 in the numerator with a secant square t dt divided by 9 plus 9 tan square t plus 16 tan square t, which is nothing but 9 plus 25 tan square t. Now I'm going to make my substitution as tan t is some other variable r, which gives me secant square t dt to be equal to dr, and my integral now gets converted to under root 3 dr divided by 9 plus 25 r square. Now this is of the form, if I take the root 3 common out, this is going to be of the form the integral of 1 divided by a square plus b square x square. Now what we can actually do is we can divide throughout by 9 in the denominator as well as in the numerator. So what we will eventually get is this root 3 common out here, 9, I take it out from the denominator, and I get dr divided by 1 plus 5 by 3r the whole square. Now, this is something that we are very, very familiar with. This seems to be of the form of tan inverse of that particular variable. So what I will actually get is, I will get this answer to be equal to root 3 by 9 and tan inverse of 5 by 3r. But then do not forget to divide by 1 by 5 by 3. So eventually, after all the simplification, I will get 1 by 5 root 3 tan inverse of 5 by 3r. So now we've got the value of the integral in terms of r. I can substitute the value of r as tan t. But remember, t was not a primary variable. Our primary variable was x. And x was the substitution we made, which was x is equal to 2 by root 3 sine t. So x is equal to 2 by root 3 sine t was the substitution we made, which implies sine t was nothing but root 3x divided by 2, which will imply tan t equal to root 3x divided by under root of 4 minus 3x square. So now I will substitute that value in this integral for tan t and get the value in terms of x. So my integral will become 1 by 5 root 3 tan inverse of, I have 5 by 3 tan t, so that's going to be 5 by 3 into what was the value of tan t? It was root 3x divided by under root of 4 minus 3x square. So these are going to cancel out. So what I will eventually get is the value of integral as 1 by 5 root 3 tan inverse of 5x divided by under root of 12 minus 9x square plus the constant of integration. A pretty lengthy question, lots and lots of substitutions here. Just pray that such questions don't appear in the advanced examination, because if they appear, there's no shortcut and you're going to use good 10 minutes to solve this question. So in this question, the objective is to find out the value of a plus b. Now, where do a and b appear? Well, we've been told that the integral of dx by 2 sin x plus secant x is nothing but 1 by under root a log of the mod of cosecant x plus pi by 4 minus cot x plus pi by 4 plus 1 by b times sin x plus cos x plus the constant of integration. So there is that a and b, and we have to find the sum of a and b. This is an integer type of question. So how do you solve this? Well, solve the integral and write the answer in terms of log of cosecant minus cot and 1 upon sin x plus cos x, and compare the coefficients of these terms to get the values of a and b. That's what we are going to do. So let's first solve this integral. If you look at this integral that is there, so you have I, which is equal to integral of dx divided by 2 sin x plus secant x. Now, when you have a secant and sine together, we never like it. So I'm going to write this secant as 1 upon cos x. And I will rewrite my integral as cos x dx divided by 2 sin x cos x plus 1. Now you have cos x in the numerator and 2 sin x cos x plus 1 in the denominator. Rewriting 2 sin x cos x as sin 2x is not going to help you, but changing 1 to sin square x plus cos square x, that's going to help you, because now you have the denominator, which is nothing but sin x plus cos x the whole square. So you have sin x plus cos x the whole square in the denominator and just a cos x in the numerator. So what I will do is I'm going to rewrite my integral as 1/2 of 2 cos x dx divided by sin x plus cos x the whole square. The reason why I do this is because if I take sin x plus cos x in the denominator as my substitution variable t, then dt will be cos x minus sin x. So I need to add and subtract sin x to the numerator. But if there is only one cos x, we will be left with the sin x independently. So because there are two cos x's, one cos x will add with the sin x, and from the other cos x, sin x will be subtracted. So that's what we are going to do. That's the trick we're going to apply. So this will be nothing but 1/2 of integral cos x plus sin x by cos x plus sin x the whole square. Well, this is an interesting integration because the numerator and the denominator are multiples of each other, and this is going to be added to 1/2 of integral cos x minus sin x. We have added sin x, so we have to subtract sin x. So that has cos x plus sin x the whole square in the denominator. So now I have already told you in the second one we're going to make use of the substitution. We're going to call this as my new variable t. So I will have dt in the numerator, and I will have t square in the denominator. I know how to integrate dt over t square, so that's going to be easy. From here, one of the denominators cancels with the numerator, and so this is another integral. So eventually you will have integral of 1 by sin x plus cos x dx, and the other place you will have cos x minus sin x by cos x plus sin x the whole square dx. So this is nothing but integral of dt divided by t square, which will simplify to nothing but minus of 1 over t. 1 over t is nothing but t is sin x plus cos x. So this will give you sin x plus cos x in the denominator. Okay, so that is set. We have solved that integral. So how do you solve the other integral? Well, the other integral has a sin x plus cos x term, and that's a standard procedure that you follow. If you have a sin x plus cos x, you divide by 1 over root 2. So you divide both the terms by 1 over root 2, which means you have to multiply also by root 2. So a root 2 gets completely multiplied to the denominator. The whole denominator will get multiplied by a root 2. So now you have the integral of 1 over root 2, 1 by, so 1 over root 2, what is 1 over root 2? 1 over root 2 is cos pi by 4, and 1 over root 2 is also sin pi by 4. So I can write this as sine of x plus pi by 4 dx. So this is nothing but the integral of 1 over root 2. Well, you have a cosecant of x plus pi by 4 dx. Well, the integral of cosec is log of cosecant minus cot. So we get the log of cosecant x plus pi by 4 minus cot x plus pi by 4 term, and we also get the 1 over sin x plus cos x term from the other side. So we have now actually got the answer which matches the format of the answer given in the question. So now it's a matter of comparing, and upon comparison you are going to get the value of root a to be equal to 2 root 2 and b to be equal to negative 2. So if root a is 2 root 2, that means a equal to 8, b is anyways negative 2, a plus b equal to 6. So that's how we solve this particular question. So for those of you who did not know that you had to multiply and divide by root 2 in that step to integrate 1 upon sin x plus cos x, you should remember that as soon as you look at the question, there is a log of cosecant minus cot, and log of cosecant minus cot is actually the integral of cosecant. So you had to somehow bring the cosecant term, and if in order to bring the cosecant term, you will have to write sin x plus cos x as something in terms of sine of x plus an angle, and that is why that entire step was there in place. Again, not a very trivial question. Lots and lots of insight is required to solve this question. Indefinite integral questions are definitely not easy. Lots and lots of practice is required to arrive at the solution, and this was yet another of those kinds of questions. So, indefinite integration is a chapter from which not many direct questions come, but whenever the questions come, the question tends to be very, very lengthy, and also the approach that is required to arrive at the answer is not very trivial. Multiple techniques of integration will be tested in a single question, as you've seen in many of the questions that I've solved. So rigorous practice is required to understand indefinite integration. So those of you who are aiming to get really good marks in integration, you should focus a lot on this first chapter of integration. Get all your techniques and skills perfected before you move on to the next 2 chapters, which are definite integration and differential equation. Remember, integration is an important section in the examination. Though not indefinite integration, definite integration is definitely the most important section of integration, and a lot of questions come from there. And to understand definite integration, you really need to understand indefinite integration. So make sure that your understanding of indefinite integration is really good, and you solve lots and lots of questions. If you've liked this video, please subscribe to our channel. Every time we make a video of this kind, you will be notified about it. So I hope you had a lot of fun in this particular session. I will see you very soon with yet another session. Until then, happy learning, happy preparing for the advanced examination.
For more videos and live lectures on the JEE, click on the subscribe button now.